You tap play on a show that 70 million people are streaming at the exact same second. It starts in about a second, in 4K, and it never stutters, never spins, never buffers. That is not luck, and it is not just a big internet connection. It is one of the most sophisticated content delivery systems ever built, and almost none of it runs where you think it does. Today, we are going to trace the entire path, from the moment a show is encoded to the moment the pixels hit your screen, and see every trick Netflix uses to make sure the video never stops. Let's start before you ever press play, back when the show is first ingested. Most people assume Netflix stores one video file per title. It does not. It stores dozens of versions of every single title. The reason is that your screen and your network are not the same as anyone else's. Someone is on a phone on a train. Someone is on a 70-inch TV on fiber. Netflix has to have a version ready for each of them. So it encodes the same show at many different resolutions and many different bitrates. That grid of versions is called the encoding ladder. But here is the clever part. For years, streaming services used one fixed ladder for everything. The problem is that a talky drama and a fireworks heavy action scene do not need the same number of bits. A simple cartoon can look perfect at a bitrate that would turn an explosion into a smear, so Netflix moved to per title encoding. Every title gets its own custom ladder tuned to how hard that specific content is to compress. Then they went further to per shot encoding. Netflix splits a movie into individual shots and optimizes each shot on its own. The still dark hallway gets fewer bits. The next shot, a chaotic fight in the rain, gets more. To your eye, the quality looks constant, but the file is dramatically smaller. And all of this is encoded across several codecs, the compression formats, the older H.264 that plays everywhere, plus VP9 and AV1, which squeeze the same quality into far fewer bytes on devices that support them. The result is a huge library of pre-encoded chunks sitting and waiting so that whoever you are and whatever you are watching on, there is already a version that fits. Now, how does your player know which of those versions to actually pull? This is the second big idea. Adaptive bitrate streaming. The video is not sent to you as one long file. Each encoded version is chopped into tiny segments, usually a few seconds of video each. When you hit play, the first thing your device downloads is not video at all. It is a small text file called the manifest. The manifest is the menu. It lists every available quality level and the address of every segment at every level. From that point on, your player is in control. It downloads the video one segment at a time, and before each segment, it makes a decision. Given the network right now, which quality should the next few seconds be? If your bandwidth is strong, it reaches up the ladder and grabs a 4K segment. If your connection suddenly drops, say you walk into an elevator, it quietly reaches down and grabs a lower quality segment instead. Same show, next few seconds, smaller file. This is why you have seen Netflix start a little blurry and then sharpen a few seconds in. That is the player being cautious at the start, then climbing the ladder once it trusts your bandwidth. And it is why the picture sometimes softens for a moment during a show without ever fully stopping. The player chose to drop quality rather than make you wait. That is the whole philosophy. Netflix would much rather quietly lower the resolution than freeze the video. A slightly softer picture you barely notice, a spinning wheel you remember. The standard that describes this menu and segment system is usually DASH, Dynamic Adaptive Streaming, over HTTP. The genius of it is that the network does no thinking. All the intelligence lives in your player, reacting segment by segment to whatever your connection is doing. But reacting to the network is not enough on its own, because networks are jittery. Your bandwidth can drop for 2 seconds when a neighbor starts a download. If the player were streaming just in time, every one of those dips would freeze the show. The fix is the buffer, and it is the single most important reason Netflix does not stall. The player does not download only the segment you are watching. It races ahead and downloads segments you have not reached yet and holds them in memory. That reserve, often tens of seconds of video sitting ahead of your eyes, is the shock absorber. When the network hiccups, you keep watching out of the buffer and you never see it. The download quietly catches up when the connection recovers. Buffering, the spinning wheel, only actually happens in the rare case where the buffer drains all the way to zero before the next segment arrives. So the real job of the adaptive algorithm is to protect that buffer. And there are two ways to steer it. One is throughput based, estimate your recent download speed and pick a bitrate that should fit. The other is buffer based. Watch how full the buffer is and let that decide. When the reserve is deep, be greedy and pull higher quality. When the reserve is running low, back off to protect it. A famous algorithm here is called BOLA, which makes that trade off mathematically. Real players blend both. At the very start, there is no history, so they lean on throughput to fill the buffer fast and get you playing. Once there is a healthy reserve, they lean on the buffer level to hold quality steady. The number you never see, the depth of that buffer, is what stands between you and the spinning wheel. Here is the problem: all of that still leaves. Those segments are real files that have to travel across the internet to you, fast, for hundreds of millions of people at once. At peak hours, Netflix is well over 10% of all downstream internet traffic on Earth. You cannot serve that from a few data centers. The speed of light is a hard limit, and every extra network hop between you and the video is more delay and more chances for congestion. So Netflix did something most companies would never attempt. It built its own global content delivery network from scratch called OpenConnect, and then it gave the hardware away. OpenConnect is a fleet of purpose-built servers called OCRs, OpenConnect appliances. Each one is basically a box stuffed with flash drives and hard drives, tuned to do exactly one thing: pour video onto the network as fast as possible. A single appliance can push on the order of 100 gigabits per second. There are thousands of these servers spread across more than 1,000 locations worldwide, and here is the key move. Netflix does not keep those servers in its own buildings. It ships them for free to internet service providers and places them directly inside their networks. Your internet provider racks a Netflix appliance in their own facility, so when you stream tonight, the bytes very likely are not coming from some distant Netflix data center. They are coming from a box that lives inside your own internet provider, maybe a few miles away. The video barely touches the public internet. It has almost nowhere to get stuck. For an internet provider, this is a great deal because it means Netflix traffic, which is a huge share of what their customers demand, stops eating expensive long distance capacity. For you, it means the single biggest source of buffering, the long congested path to a faraway server, mostly disappears. But putting a server inside every internet provider only helps if the right video is already on it when you press play. An appliance a mile away is useless if it does not have your show, and you cannot fit the entire Netflix catalog on every box. The catalog is enormous. The appliances in your city can only hold a slice of it. So which slice? This is where prediction comes in. The content is loaded onto the appliances ahead of time, during quiet, off-peak hours, usually in the middle of the night when almost nobody is streaming and the network is idle. Netflix calls this the fill window. No one is watching, so the appliances spend the night quietly downloading tomorrow's shows. And Netflix is remarkably good at guessing what tomorrow's shows are. It knows what is trending in your region. It knows what people added to their lists. It knows that a new season drops Friday and that it will be hammered all weekend. So the night before, that season is copied to the appliances near you. Before a single person hits play, the most popular titles get pushed to nearly every appliance because everyone will want them. The long tail, the obscure documentary 3 people in your city will watch, lives on fewer, larger servers a bit further out. It is a hierarchy. If your local embedded appliance does not have something, it pulls from a bigger site at an internet exchange. And only as a last resort does anything come from the origin storage back in the cloud. So by the time you are scrolling the app in the evening, the war is already won. The video you are most likely to choose is sitting on a drive inside your internet provider, waiting. Press play, and it is right there. Now the moment of truth. You press play. How does your device know which of those thousands of appliances to talk to? This is where Netflix splits cleanly into two halves, and it is the most important architectural idea in the whole system. There is the control plane and there is the data plane. The control plane is the brains. It runs in the cloud, on Amazon Web Services, your login, the home screen, your recommendations, search, billing, the play button itself, all of the logic that decides what you see. The data plane is the muscle, that is OpenConnect, the appliances doing nothing but shipping video bytes. The two almost never mix, and that separation is deliberate. When you press play, your request goes to the control plane in the cloud. A service there, the steering service, does the matchmaking. It looks at who you are, where you are on the network, which internet provider you are on, and which appliances near you actually have this title already cached and are healthy right now. Then it hands your device a ranked list of specific appliances to stream from, best choice first, with backups. Your player tries the top one. If that box is busy or slow, it silently falls to the next on the list. Notice what just happened. The cloud made a smart decision once, in a few milliseconds, and then completely stepped out of the way. It does not touch a single frame of the actual video. The bytes flow straight from a nearby appliance to you. That is why the system scales. The expensive thinking happens once, upfront in the cloud. The heavy lifting, moving petabytes of video, happens on cheap dedicated boxes sitting close to you. There is one more thing standing between you and a frozen screen: failure. At Netflix's scale, something is always broken. A server dies, a whole data center has a bad day, a new release goes out with a bug. With hundreds of millions of members, you cannot promise nothing ever fails. So Netflix promises something better: that when things fail, you do not notice. The philosophy is famous. Instead of hoping failures do not happen, Netflix causes them on purpose. They built a tool, Chaos Monkey, that randomly kills live servers in production during business hours. The idea is brutal and brilliant. If a random server dying can take down your service, better to find out at 2 in the afternoon on a Tuesday, with engineers watching, than at 9 at night during a finale. So every service is built assuming its neighbors can vanish at any moment. The control plane runs across multiple independent cloud regions. And if an entire region falls over, traffic fails over to another one. And when something does break, the system degrades gracefully instead of collapsing. This is the crucial part. If the recommendation engine is down, you still get a home screen, maybe just showing popular titles instead of personalized ones. If a fancy feature fails, the play button still works. Netflix will drop personalization, drop artwork, drop almost anything before it will ever drop playback. Circuit breakers wrap the calls between services, so one slow component gets isolated instead of dragging everything down with it. The failure gets contained in a corner you never see. That is the difference between an app that occasionally has a bad night and one that 70 million people can lean on at the same instant. So let's put the whole machine together and watch a single play click travel through it. You tap play. In that instant, your device talks to the control plane in the cloud. It checks that you are allowed to watch, and it gets back a license, the key to decrypt this protected video. At the same time, the steering service picks the best Open Connect appliances for you, the ones inside your internet provider that already have this exact title from last night's fill. It hands your player a ranked list of their addresses. Your player fetches the manifest, the menu of every quality and every segment, and opens a connection to the top appliance on its list. Now the adaptive algorithm goes to work. To start fast, it grabs the first couple of segments at a modest quality, because getting you playing quickly matters more than starting in perfect 4K. Those first segments come off a flash drive a few miles away, so they arrive almost instantly and the picture appears. While you watch those opening seconds, the player is already racing ahead, filling the buffer and measuring your bandwidth. Once it sees the reserve building and the connection holding, it climbs the ladder, and the image sharpens to full resolution. From here it just maintains. Keep the buffer deep, hold the quality steady, quietly drop a rung if the network wobbles, climb back when it recovers, segment after segment, out of a box that lives inside your own internet provider. Encoding, adaptive bitrate, the buffer, open connect, predictive fill, the steering service, and graceful failure. 7 systems, all firing in the second between your tap and the first frame, all with one shared job: make sure the video never stops. That is the real trick. Netflix is not really a video website with some servers behind it. It is a globe-spanning delivery network with a video catalog attached, engineered from the encoder all the way to a box in your neighborhood, so that the moment you press play, the answer is already sitting a few miles away. The buffering wheel did not disappear by accident. It was designed out one system at a time. If you want to see how another giant solves the same delivery problem from a completely different angle, that is where we are going next. Subscribe to CloudCraft so you do not miss it. And if this made the magic make sense, send it to the one person you always argue with about which streaming service buffers less. Now you can actually win that argument.